Well, hi there, everybody. I'm not going to give you my usual song and dance about how excited you are because I know how excited you are, as am I, no doubt. Overnight, your run has been running, as mine has, and you're eager to see the results. But we have some content to do first of all. So, already you can do so many things, coding against frontier and open source models, using dataset curation, baseline and fine-tuning frontier models, and now running QLoRA. So today I had previously said there were going to be 2 bullets, but I have put in an extra bullet here, beginning here with how training works. It occurs to me that I've been quite hand-wavy about the training process itself. And at this point, now that you've got some hands-on experience running training, seeing QLoRA in action, it's worth me just taking a minute to explain it properly. So you've got that basis. You may know it all already. It might be something that at this point you've either picked up or you already had encountered. Either way, I think it's super important that I do clarify that. And so we'll take a couple of minutes to do it. And I think it's really nice that you've had some experience first running training so that this will hopefully connect the dots and things will click in place. We will then run inference for a fine-tuned model, and then we will have the conclusion of week 7, which is exciting indeed. All right, let's get started. So, I want to explain that the training process, the process of improving a model so that it's better and better at performing a task, is something that has 4 steps to it. The first step is what's known as the forward pass, which is just another name for sort of running inference. You have a point in your data set, you have a particular training data point, and you take that training prompt and you pass it through your neural network to get the prediction for the next token. And that is called the forward pass because you're thinking of the input coming in, going through, and the output popping out at the end of your transformer. There is then what's called the loss calculation. And we'll talk a little bit more about this later, but this is saying, okay, so the network predicted that this would be the output. And in fact, this is the true next token because we're in training. And so we've got real examples that include what actually did come next in the data. And so now that you've got the prediction and the truth, you can come up with some way of calculating the loss, or how wrong were you? How bad was it? Loss being the sort of inverse of accuracy. So a bigger loss number means things went worse. So that's step 2, the loss calculation. Step 3 is known as the backward pass. And you hear different terms for this. It's called back propagation. And the idea is that in this backward pass, you take this loss and you look back through the neural network and you ask the question, if I were to tweak each of the parameters in this neural network by a little tiny bit, would it have made this loss bigger or smaller? How is the loss dependent? How is this particular weight? How does that vary the loss? What's the difference in loss based on this weight? And that sensitivity is called a gradient, of course, as it is generally in maths. And so this is about calculating the gradients of all of your weights to see how the loss is affected by a small tweak to those weights. So that calculating the gradients of all of your weights is known as the backward pass. And then finally, the 4th step, optimization, is, and this is the thing that we selected, the Adam with weight decay, the Adam W optimizer for our particular training exercise. Optimization is saying, okay, so now we've calculated all of our gradients. What we now want to do is we want to tweak all of the weights a tiny, tiny bit, such that next time, if it were given the same prompt, it would be more likely to do a little bit better. The loss would be a little bit lower. So we're going to tweak in the direction, the opposite direction to the gradient, so that losses would be reduced. And that small step, which is based on the learning rate. How much of a step you take is based on how big the learning rate is designed to make things a little bit better. And you always want to try and do it in a way that will generalize well. You don't want to just be solving for exactly this input prompt. You just want the model to be learning to get a little bit better with those kinds of prompts in the future. And of course, all of this process happens with mini batches at the same time, and it happens again and again and again. All the way through your data is one epoch, and then potentially another time and another time after that, as it goes through multiple epochs. So that repeated process is what is known as training. And now in the next video, we will just step through a diagram to illustrate that. And now let me make this real for you by showing you some diagrams, particularly now looking at how training works with QLoRA, which is how we're actually doing it in practice. So first of all, let's talk about this forward pass. So here is a diagram that should be familiar to you because it's the same one I used before, that shows our Llama 3.1 base model that we've quantized all the way down to 4 bits with its 8 billion parameters. And the white, all of it is frozen. We're not going to be changing its weights as part of training because it would be way too much work, way too much memory, and too slow to try and shift and tweak and optimize these 8 billion parameters. So what we're seeing here is a bunch of frozen rows of weights, and the ones in yellow are also frozen, but they're representing our target modules, which QLoRA is going to be applied to. And let's bring in our LoRa adapters. There they are. You may remember that, to be technically correct, there are in fact 2 adapters called A and B for each of the different target modules. They have dimensionality given by R, and you may remember that alpha is the scaling factor, and it just is as simple as the way that these are applied to their target module is that it's alpha times A times B. Simple as that. So that is our neural network that we know well, and we are going to be training the weights in these LoRa adapters, which in our case is about 109 megabytes worth of weights. Okay, so then what happens? We have an input prompt over on the left. It is like price is dollars, and then it's the next token we want the model to get good at predicting. The forward pass is when we take that and we, in inference mode, basically, we take it through the model to say, please predict the next token. And so that goes through the model, and what comes out the other side is a predicted next token. Price is, and then 99. And again, because we're taking advantage of this simplicity of Llama 3.1, that in fact 99 is just one token, and that will always be the case for any 3-digit number. That's not that that's critical, but it does simplify things a bit for us. So that's the forward pass. All right, now on to the loss calculation. So here we are again. We've predicted the next token. So now the model is able to look up the training process, the SFT trainer in our case, looks up what was the actual next token, because we've got the training data. We know the actual next token. And what was it? Let's say it was 89. It was lower. So we were wrong by $10. Or wrong by a different token. It doesn't know that this represents $10. It just knows it's a different token. And so there is some kind of a loss. And in just a moment, I'm going to explain what that loss is and why it's not quite as simple as it just being a different token. There's a technicality there that we'll get to. But for now, you can just think of it as it predicted 99. The actual value was 89. We have a loss. So that's the loss calculation. Step 3 is the backward pass that you hear people calling backprop or backpropagation. And in backprop, basically we look back through the network, back we go, and we say, all right, so how much, if we were to tweak these weights by a little bit, how much would that affect the loss? How sensitive is the loss to those weights? It gives us what we call the gradients of the weights of the parameters. So when I say weights, they're synonymous with parameters. What are the gradients? If we were to change those weights, what would it do to the loss? Because we want to try and improve things a little bit. And so those red triangles are meant to represent delta for showing like a gradient calculation that's happened there. And then finally, we get to the last step, step 4, optimization. Here it comes. So we've got these gradients. What we now need to do is we want to take a tiny step in the right direction. So we want to update the parameters in our LoRa matrices a little tiny bit so that next time, if it gets the same input prompt, the loss will be a bit lower. It would do a bit better. So we're taking a step in the right direction, and we use the learning rate to decide how much of a step to take. Because as I said before, there are pros and cons of taking smaller or larger steps. And you may remember that the optimizer we're using, the Adam W optimizer, does something quite cunning where it doesn't just use these gradients. It keeps a kind of rolling average of prior gradients so that it's being really smart about how to take that step in a way that's most likely to improve things. And it's also trying to make sure that we don't do things like overfitting and other dangers that we've talked about before. So we do that. And what happens is that the LoRa adapters are then improved. And as they are applied in the future to our base model, it will do slightly better. The loss will be a bit lower next time. And that is why you see that the training loss is coming down in our wiggly charts, because it's learning and getting better and better. And so it's worth noting, of course, that the weights, the parameters that get changed are the parameters in the LoRa adapters, the green ones. We don't actually change any parameters in the Llama 3.1 base. That is just too big, too many parameters. If you were doing ordinary training, fine-tuning, not LoRa based, but ordinary, then it would be the whole Llama 3.1 model that would need to be having gradients calculated and need to be shifted during optimization. And that, of course, is what these big companies like Meta, that's how they've trained Llama 3.1 in the first place. And they've spent significant amounts of money doing it, which we don't have easy access to, which is why we're using our LoRa adapters instead. So that's the quick summary of optimization of the whole of the training process. And I imagine that was probably mostly clear to you already, but I'm hoping that these diagrams have crystallized it for you and mean that everything has fallen into place. And in the next video, I'm just going to explain one more technicality, a very important technicality about what we mean by the prediction and the loss calculation. See you then. Take one more moment to look at this very nice diagram that lays it all out, and we will move on now to the technicality that I wanted to mention. So, I have been a bit loose in the past when I've said that the model predicts the next token, which is one way to think about it, one simple way to think about it, and we often use that turn of phrase. But it's not what's actually going on. It's not like you have a transformer architecture and the bottom layer, what comes out of that, is a single token, which is the predicted next token. That's not how it works. What actually comes out of the last layer is probabilities. It has every single token, and for every token, it has what is the probability that that is the next token. It outputs that series of probabilities. That's what comes out of the bottom of the neural network. You may remember there was the last layer that we saw when we printed the model is called LM head. And that is really the very final step that comes out. It actually comes out with a vector of numbers that are known as the logits, which are that represent the probabilities. And you need to put that through a function. This is getting probably too much detail now, but you may know it already. There's a function called Softmax that converts these numbers into what can be thought of as probabilities, because each token will then be somewhere between 0 and 1, and they will all add up to 1. So it gives you a way to interpret the results of the model as a probability of each possible next token. So that is actually what comes out of the forward pass. When you're doing inference, when you're running this in inference mode, So what you get out of it is then all of these probabilities. So what do you do with that? How do you say what next token it's predicting? Well, most of the time, actually, it's a very simple approach. You simply take the most likely next token. You take the token with the highest probability. It gave you all these different probabilities. Find out which one is the max. Take that one as the next letter. There are other techniques that are a little bit more sophisticated. You can sample randomly using these probabilities as your weight for how you sample. That gives you a bit more variety. And there are some other techniques you can use to sample a few letters in a row and then decide whether that's the path that you want to take. So there are a bunch of different strategies during inference that you can use based on these probabilities to do the best job. And in fact, when we go and look in our project in a second, we are going to use a slightly non-standard strategy. Since we know that this token represents a cost, it represents a number, we can do something a little bit smart with it. But that's not necessary. You can also always just simply pick the one with the highest probability. So that's model output really explained. I hope that's now crystal clear for you. And then the loss function. So I slightly glossed over in the last video, like you calculate a loss. How bad was it? So what does that actually mean in practice? It's wonderfully simple. So we've got these probabilities of all of the possible next tokens. So what you do is you say, okay, well, we actually know what the next token was supposed to be. Let's say it was supposed to be 99. So you look up in all of these probabilities and you say, what probability did the model give for 99, for the thing that actually was the right next token? And that's all that matters here. All that matters is what probability did it give to the thing that was actually correct. If it gave that a 100% probability, then it was perfect. It was 100% confident in the right result, and everything else would have to be 0 because probabilities all add up to 1. So that would be absolutely perfect. If it's anything less than 100%, then it didn't do well, and the lower probability it gave, the worse it did. So you take that probability, and then it just turns out that the formula that seems to work well is to take the log of that number and then negate it. So you take -1 times the log of that number. And if you work that out, that means that if that number is 1, if it's 100% probability, then you get 0. And that sounds good because you want 0 loss. Loss should be nothing if you were perfect. And then the lower your probability is, the worse, the higher that loss number will be. So taking negative log of the probability is a way of having a good, well-behaving loss function. And there's a fancy name for it. This loss function is known as the cross-entropy loss. That's what they call it. It's just negative log of the probability of the true next token. And that's what's used. And that's what's being used right now. If your training is going on, it is calculating the cross-entropy loss for each of the predictions. And there's another side note, there's an interpretation of this, particularly for data scientists amongst you. This is the calculation that's used for classification when you're trying to classify something into different bins. If you've got, like back in the day when there were times when we were trying to classify images to be one of 4 or 5 different categories, cross-entropy loss, you come up with a probability and you use cross-entropy loss to figure out whether or not you've done a good job of classification. And in fact, that makes sense because the whole process of predicting the next token is really a classification problem. You're just trying to say there are many possible categories of that this next token could be. In fact, there's all of the possible next tokens. And we're going to predict which one is the most likely bucket to put for the next token. And so the whole process of generative AI is really just a classification problem, classifying the next token, figuring out the probability that the next token is what it turns out to be. And so interestingly, for our particular project for predicting model prices, it's really, as I said some time ago, it's really a regression problem. You're trying to predict a number, and we're treating it like a classification problem, which is okay because it's really going to turn out to be just a number between 0 and 999, between 1 and 999, which are just 999 different possible buckets. And we're just trying to classify effectively every product into one of these 999 buckets. And that's why it works quite well as a classification problem. And it's why the frontier models are good at it. and why we're hoping, fingers crossed, that our open source model is going to be good at it too. And with all of this, some good, useful theory behind us, but now it's time to get back to some practice. So with that in mind, it's time for us to talk about how has our open source fine-tuning been going. Here we are back in the collab, which has been running overnight for me and probably for you too, I hope. And if anything like me, you've been eagerly glued to it. So this is showing the part in the collab where it's running away, and you can see it's ticking through. It's more than halfway at this point as it makes its way through the 4 epochs. 4 epochs are not required for this. You only need to do 1 epoch, of course, and just that I'm a sucker for this stuff and loving it. So it's ticking away. Let's go to the fabulous weights and biases to see how it looks here. This is our run. You remember in weights and biases, the navigation at the top here lets you see the different projects that you may have. And we're looking at my Pricer project, which is the one in question. I've also got a Pricer GPT project for where we fine-tune GPT. And then here are the different runs. I name the runs in the code after the date and time that they were kicked off. You don't need to do that. You can call the runs anything you want. I do this because it helps me be able to recollect when I did what run and so on. So I found this quite a useful trick. But you could also name it to describe the kind of run that you're doing. And you can also rename it by right-clicking on it. So the current run is this blue run right here. This is what we've been running. And if I zoom in on the training loss, which is the diagram that really matters, you now know this is cross-entropy loss we're seeing here. And you'll see that it clearly has, this was the first epoch. It comes down a bit here, potentially because some overfitting starts to happen when it sees the data a second time. And then it drops again for the beginning of the 3rd epoch here. The thing that I'm not doing, that is very much a best practice that I should be doing, is having a validation data set, and we'd be able to see validation loss. And I imagine what you'd find is that it maybe only decreases a little bit here, and maybe quite soon it will start to increase a bit because we are overfitting. We'll find that out by running the model in inference mode, but it would be better to see the validation results, and hopefully that's something that you are doing. And I would love to see those charts, by the way. So what we can also do is layer on top of this the prior run that I had done when I ran it through to completion. Here we go. Let's zoom in again on both of these runs together. And what you'll see is that the 2 runs are very, very similar indeed. Obviously, I had the same the same hyperparameters, and I'd set random seeds, and so it's not a great surprise, but it does show you that despite all of the complexity and everything that's going on, you do get the same numbers from these runs. So that's somewhat comforting, and I think that's probably all to show you. We can see that in terms of the learning rate, that now, while before we were suspicious that the blue line, if we just look at the blue line only, it just for a moment flashed up with what it used to be if you saw that. If we bring this up, you'll see that last time it was all the way up here, and maybe you were skeptical about whether we were really seeing a nice smooth curve, and now you clearly see that it's coming down in a very nice way. So the cosine learning rate scheduler is a good trick to know, a good way to vary the learning rate during the course of your batch. Okay, and then final thing to show you is to flip to Hugging Face. I'll mention, if you look at this model, you'll see that the name of this ends in 11 seconds, that timestamp. If we go over to Hugging Face in the hub, I've got all these different models, and this one ending in 11 seconds is, of course, the running question that's running right now. And in fact, it even says updated 2 hours ago, so we know it's the right one. As I say, some people would just have the single repo that they'll just write to for all of their different runs, and that's a perfectly good way of doing it. I prefer doing it this way, so I keep my different runs completely separate. And if I go into this repo, we're now looking at, if I click on files and versions, these are the files associated with this run. Again, the safe tensors, that's the business. That's where it all happens. It's 109 megabytes worth of parameters that are the parameters of our LoRa adapters. And over here, you'll see history 9 commits. If I click on this, it's showing me that just as I had asked in my parameters, in my setup, Hugging Face has been saving this to the hub, uploading it, making a different revision of these model weights every 5,000 steps. And so that's something we'll have access to if we want to go back and do some do inference on any one of those different commits. And hopefully you can see why I like to keep it as a separate repo, so I don't muddle up the different saves during a particular run with the different versions of training. Okay, I think that's enough of a tour of where we're at. Head back to the slides one more time before we actually get to inference. So before we try our new model, and one more recap on the models so far, and keep notes of this so we can see how we do and your excitement can be there while we run our fine-tuned model. We started with a constant model. We actually started with a random model, but I think we can put that one to bed. That was silly. So a constant model, which just guesses the average from the training data set, ends up with an error of 146. And we certainly hope that we can do better than 146. Otherwise, we might as well stick with a constant. When we used a very simplistic traditional machine learning with basic features, we got 139. You remember that well, I hope. Random forest, a more sophisticated algorithm that also that looked at the language, the words, got down to 97. This human did a poor job at 127. GPT-4 the big guy, did very nicely indeed at 76. And the base Llama 3.1 untrained, quantized down to 4-bit, did an appalling $396 of error. I'm much better off just sticking with a constant than using an untrained llama. The poor thing did not do particularly well at all. So I go through this one more time so that you have this nicely framed. The question is, remember, GPT-4 is a model that has trillions of weights. GPT-4 had 1.76 trillion. GPT-4, it's not known, but it's considered to be much more than that. So a huge number of weights. Llama 3.1 base has 8 billion weights, and we have reduced them down to 4 bits. And then we have used our QLoRA, our LoRa adapters, like 109 megabytes worth of them, to put some extra weights that we can use to adapt Llama 3.1 base. But these are still small numbers. And obviously, this is an open source model, which means it's free to run. So I'm saying all this to set expectations that obviously it's a lot to ask to try and compete with some of these models at the frontier. The thing that you need to be looking out for is, can we do better than traditional machine learning? Can we do better than a human? Certainly, can we do better than constant? And how do we stack up when we compare ourselves to GPT-4o, the leading frontier model? And we can also compare it to GPT-4o mini as well afterwards. So that gives you the context. I hope you have this in your mind. Maybe write down the numbers so you're ready for what's to come. And it is time for us to head to Colab and to run inference on the best, the strongest checkpoint from the training of our own verticalized, specialized open source model. Here we are back in Colab looking at the week 7, day 5 of the Colab notebooks. And I'm on a T4 box, so it's a low-end, cheap box. That's all that's required since we are doing inference today, not training. Although training is still happening in this other tab, as you can see as we speak. We start with a few installs and then some imports with the usual kind of stuff. And let me just tell you about the constants that we've got here. The base model, of course, Llama 3.1. Project name is Pricer. The Hugging Face user, so you choose here. You can put in well, I hope that you'll be putting in your name and you'll be running this inference, this test against the model that you have fine-tuned and uploaded to the Hugging Face Hub. It is possible, though, that you have either lost patience or you just want to see how my one did, in which case you can keep my name in there because this model will be public, so you will be able to run against this model too. And I've selected in here the run name. This is the run name. You may recognize that 39 there is the run name in Hugging Face of the one that I ran for multiple epochs in the past. And this revision, this is where I am specifying which of the different checkpoints I'm selecting. I'm selecting the one before it started to badly overfit. And this was the one where it was still getting good results. And then this becomes the name of my fine-tuned model. It is, of course, the Hugging Face name. I'm sorry, I should make this, otherwise I'm hard-coding my name in here. But what I'll do is I will make two versions of this. One will be for the Hugging Face user that you have entered in. And the other one I will comment out. And I will say, uncomment this line if you should use my model. And either, of course, if you're using your model, you'll need to change the run name and the revision to match whatever you're using. And you can start by not putting in, put revision equals none, or revision equals none if you're not using a revision at all. Okay, and then for the data set, either, again, we load in the data set that you have carefully, lovingly curated and uploaded to the Hugging Face Hub, or you can just use my one, should you prefer. And now, and by the way, if you have gone with the lower cost version of this and you've trained your model for appliances only, for home appliances, then of course you should be filling in the light data set that you'll have built and your model for home appliances, and you will get similar kinds of results. Quant 4-bit is true, we are quantizing, and then you may remember these are the nice ways that we can print colorful lines to the output. Okay, then we log into Hugging Face. You're used to this now. We don't need to log into weights and biases because we're not training. And then we load in the data set. And as well, you know, at this point, if I look at the first training data set, we won't be using it anymore, but it has the price baked into it. It looks like this. We will, of course, now be using the test data set, which looks like this. The text does not have the price. The price is only in the answer, which is not given to the model. It's only given this text. As you can double, triple check in a moment when we get to the part that will be actually doing this prediction. It would be a bit of a gaffe, wouldn't it, if we were accidentally passing in the price itself, but we're not. Okay, so then first of all, it's time to load in our tokenizer and our fine-tuned model. So we first pick the right kind of quantization. You're familiar with this, same as before. This is also the same as before, well, with a slight difference just here, but we load in the tokenizer, we put in that boilerplate stuff to set up some of its parameters. We load in the base model as before using the right quant config, and we've got that one-liner again. And now this is new. So we are now loading something called a PEFT model. PEFT, you'll remember, stands for Parameter Efficient Fine Tuning. It's the name of the package which has coded LoRa. So a PEFT model represents, it's a Hugging Face model that represents a model that has a base, and then it's got some adapter applied on top of the base. And so that is what we load now. You call that with from pre-trained, and you can pass in the base model, the fine-tuned model name, which we set up above, and then a revision if you wish. So if revision is not null, none, then I pass it in. Otherwise, we just don't bother passing it in. And so that will load in our fine-tuned model. And at the end of that, we'll print the memory footprint. You may remember the memory footprint was what, 5.6 gigabytes before, and now it is 5.7. It's 5,700 megabytes because there's that extra 100 megabytes or 109 megabytes of our LoRa adapters, our LoRa A's and LoRa B's in there. One more time, we can just print this fine-tuned model. You may remember we did this right back in in day 2 when I mentioned we were taking a look into the future. I was using this model itself was the one that we looked at, and this is how it appears. If you remember this, you can see all the different layers of the neural network, and you can see that when you get to these the tension layers, that there's a dropout layer in there now. You know all about dropout with 10% probability of dropout, and then there's LoRa A and LoRa B that are in there as well. Yeah, you can see that LoRa A and LoRa B are for all of the layers that have been adapted, our target modules. And you also worth just noting down at the very end here, the LM head, since I just talked about that, this is the final the final fully connected layer that outputs the logits, the number for each of the possible token vocab entries, which will then go into a softmax in order to predict the probability of the next token. All right. Are you ready? So we're going to go in and run inference. I want to give you one more time a quick memory that GPT-4o got to $76. Llama 3.1 base model, this untrained model, was $396, very disappointing. This human being here got 127 as my error, and very much hoping to see that Llama can beat a human as an open source model. It is important to keep in mind, in case you're expecting something crazy here, that prices of things have a lot of volatility, and the model doesn't know anything about that. It's not going to know if the price of a product has been slashed because it's on sale by a huge amount. So there is a natural big variation in these product prices, as I discovered when I was trying to do it for myself and got wildly out. It's a very difficult challenge. You might think that it sounds like it's not that hard. It is very hard. Try it for yourself and you'll see. Okay. With that caveat in mind, let's keep going. So extract price is the function that you know well. It takes a string, it looks for price is dollars, and then it finds the number that comes at any point after that. One more time, let's just satisfy ourselves. Extract price and put in a string. Price is dollars, a fabulous 899.99 or so. Whatever I want to say, and out comes the price. I'm sure you get it. So that's extract price. And then this is the model predict function, the function that we used before that takes the inputs, that takes the attention mask, is that thing I told you about that you use to avoid it throwing a warning and to make it very clear that we don't need it to predict the most of the input prompt. And then the outputs we call generate on the fine-tuned model. We pass in the inputs, pass in this attention mask. We only need up to 3 new tokens because we're going to get the next token is really going to be the one that we care about. But we'll put in some more just to make sure if it makes some horrible mistake that we capture that. And then we say only one response, please. We take that one response and we extract the price. Now, as it happens, we can do a little bit better than this prediction function. This doesn't make a whole massive amount of difference, but since we've got so much control over this model, we can actually do something a bit smarter with how we handle this next token. And so I've written this function that's an improved model predict function, improved model predict, which is, it's just, it's a bit more involved. I guess I'll just explain it in simple terms, but it's not super important. What it does is, instead of just taking the most likely next token, it takes the most likely 3 next tokens, the 3 with the highest probability. And then it says, okay, what probability did you give for these 3? and they represent real numbers. Like maybe you said it was very likely to be worth $100, and then a little bit less likely to be 99, but a lot more likely to be 101. But 100 was the most. And then it just takes a weighted average between those three numbers. And that's a way for us to get a little bit more precise about what's it trying to predict. And it allows it to predict something that's not necessarily always a whole number. So it's a technique I've used. It's sort of solving for the fact that we're treating what is really a regression problem as a classification problem. It's not super important that you know about this, but and it doesn't make much difference if you use the function above. It just makes a bit of difference. But it is maybe worth looking through this if you're interested in these last layers of the neural network, because you can see that what I do is I take the outputs of the fine-tuned model, passing in the inputs, and these are considered the logits that I mentioned, this vector across all of the possible vocabulary entries for a tokenizer. And then I call Softmax in order to convert that into probabilities. And then I go through the top three, and this is some gumph that just takes the weighted average between those top three. It's weighted prices and sums up the weighted prices, and that's what it returns. So it's very similar to model predict. It just gives a slightly more accurate answer that's based on the top three predictions, not just the top prediction. And so then we have our class tester. This is just exactly the same tester class that we've used before. And it is worth just pointing out that the thing I mentioned before, this is the meat of the whole thing. When we take whatever functions passed in and we call it, and what we pass in is only the text associated with the data point. We obviously don't tell it the price. All it knows is the text, so that it doesn't have any knowledge of the price, of course. And then we then just call tester.test. Well, I'm going to use the improved function, and we pass in the test. And like some kind of a soap opera, I'm now, of course, going to say, we will get the results of this in the next video. I will see you there. So like an episode of X Factor, I left you hanging at the end of the last video with the results of our model. And here we go. We are now going to look at the results of our open source model fine-tuned for the problem of predicting product prices. So it starts with a green result out of the gate, and then a yellow one, green, yellow. But then a fair sea of greens, yellows, greens are red, green. Hang on, hold your horses. Here we go, back over here. And plenty of greens here, some reds. It's looking promising though. Let's scroll all the way down now. And here is the result. The metric for the accuracy of our model is 46.67. 46.67. That means that we have stunningly beaten Frontier GPT-4 with its trillion plus parameters with our tiny 8 billion quantized model. We have outperformed the Frontier for this problem. That is fantastic. I can't say that enough. I was so thrilled when I first saw this, and I hope you are too now, and hopefully you're seeing it for your own runs. This is a tremendous result. Look at this diagram. Look at how scroll down a little bit so we see it in its full glory. See how closely it has been able to predict results against the blue line of ground truth here. It's done such a spectacular job. Yeah, when I say that this is a low number, remember, I'm not sure that you can do very much lower than this, given that prices of products vary quite a lot just naturally. So this is just really, really staggering. And it's just so very exciting that this isn't just better than traditional machine learning. It's not just better than a human. It's also better than frontier models that are out there today. And of course, we've achieved that because we've taken this smaller open source model and we've fine-tuned it to be particularly effective at this particular problem. If we try and ask it to compose poetry, it's going to do a horrible job. If we ask it to predict the prices of products, it is going to be outperforming other models out there, including GPT-4 and Claude. So I am so very happy about this. I do hope you are as well, and that you share in my enthusiasm for this moment. This is what it's been leading up to. We've built a model that outperforms the frontier. It's something to be very proud of, and we'll, in the last video, put it on a podium and see how it stacks up. Let's now see our results side by side. We started our journey with a constant model that was at $146 error from the average of all of the data in the training data set. We looked at a traditional machine learning model with just a few features. It got to 139, it beat the average. Random forest, the best of our traditional machine learning models, got to 97. The human got to 127. GPT-4 got to 76. And our fine-tuned, customized model has got us to $47. And this, of course, brings me to the challenge for you. The challenge for you is to improve on this $47. This is something where hyperparameter optimization can go a long way. And so the task in hand is now to play with the hyperparameters, experiment, use weights and biases, explore maybe different optimizers, different learning rates, different batch sizes, and see what you can do to improve on this number. You can also explore different ways of running the model at inference time to see if that improves it. And then there is one factor that is actually perhaps the way that you can make the biggest impact on the results with the smallest change is to relook one more time at the data set, at the data curation step, and challenge yourself to see whether you can think of different ways to be prompting or organizing that information in order to be getting better outcomes. And then there is one final thing that you could do, which is a bigger step, but very exciting. And if you don't do it, I'm definitely going to do it, which is to try the other models on this. Try Gemma, try Qwen, the powerhouse, try Phi3. See how they perform. There are a couple of places where it might be a bit fiddly because they might not predict one token as the right number. Just maybe that's only at that inference function. Otherwise, everything else might just be fine. But you'll need to experiment with that and convince yourself that it's good. So try some different models. You could also try doing the whole thing with a version of Llama 3 that's quantized to 8 bits instead of 4 bits, depending on your appetite for that. There are also some larger models. There is a version of Phi3, I think that is 14 billion parameters that you could experiment with and see whether that improves things. So that is the objective. I would love to hear from the first person that can get this below 40. That has to be possible. I think there is like a hard limit on how low you can get it, given the reality of uncertainty in pricing. But I think you guys, someone is going to be able to get it below $40. You'll build a model that can get within $40 across the 250 first items in the test set. And I can't wait to hear about that. So please do reach out and tell me when you get below 40 and tell me your hyperparameters in your model so that I can try and recreate it myself. I would love that. And with that, let's wrap up for the week. It's the end now of week 7. What you can now do, of course, obviously generating text and code with Frontier APIs and with open source models and Hugging Face. You can solve problems, including dataset curation, a baseline model, and fine-tuning. And at this point, you can confidently carry out the full process for selecting and training an open source model that can outperform the frontier. And that's a big accomplishment. So next week is the finale of this course, and I promise you, I've kept the best to last. It's going to be a triumph. Next week is going to be so much fun. You've got this far. Hang on in there to the very end to see everything come together. There's some stuff that's really important we're going to do about now packaging up what we've done and being able to deploy it as behind an API so we can use it for production purposes, and then really package everything into an application that can make a real impact. And at that point, you'll be in a position to be creating your own end-to-end solutions to commercial problems using groundbreaking LLMs that you'll be able to train yourself. So there's a lot ahead, and I can't wait for next week. And as always, I will see you there.